Hi everyone, I'm Whitroy. Today my colleague John will present a lesson about the MEN system used in New Zealand. Before John begins, I would like you to think about three simple questions. First, imagine that an active conductor inside an appliance touches its metal case. Most students know that the MCB should trip. However, can you draw the complete fault circuit? Where is the power source? Some students think the power source is the socket outlet or the main switchboard, but these answers are incorrect. Second, what is the main purpose of the earth electrode? Some students think the fault current normally travels through the earth electrode and the soil. Is that correct? Third, why do we need the MEN link? Why are the neutral bar and earth bar connected at the main switchboard? What does this connection actually do? John will answer these three questions throughout this lesson. More importantly, he will show you how to analyze the MEN system using knowledge you already have, including a simple AC circuit, a complete current path, and Ohm's law. Now let's begin the lesson. Over to you, John.
Hi everyone, I'm John. Today we are going to build a clear picture of the multiple earth neutral system, usually called the MEN system. Let us begin with one simple fault. Inside a metal cased appliance, an active conductor becomes loose and touches the metal case. The active is now connected to the case. I ask the class, what will the circuit do? Many students answer, the MCB will trip. Good. Then I ask, why will the MCB trip? The answer is often, because there is fault current. That is also a start. But now comes the important question. Can you draw the complete circuit followed by that fault current? Can you show where it leaves the transformer and exactly how it gets back to the transformer? And can you use Ohm's law to estimate how much current will flow? If we cannot draw the closed circuit, we do not yet know the total impedance. If we do not know the impedance, we cannot calculate the current. And if we do not know the current, we cannot properly explain whether the MCB will trip or whether it will trip fast enough. So this lesson will not begin by asking you to memorize the sentence, an earth fault trips the MCB. We will begin with the simplest AC circuit you already understand, a voltage source, a complete conducting loop, and impedance. At 50 Hz, we use the AC form of Ohm's law. Current equals voltage divided by impedance. I equals V divided by Z. Then we will expand that simple circuit. We will add the appliance case, protective earth, earth bar, MEN link, supply neutral, and transformer. Later, if the MEN link is missing or a connection has high resistance, we will redraw the circuit, change the impedance, and calculate again. The same basic method answers the advanced question. That is what I mean by the big picture. The big picture is the framework that connects a new MEN problem to circuit principles you already know. Every part must fit into the complete circuit. Every prediction must follow from the current path, the impedance, and Ohm's law. By the end of this lesson, you should be able to place the MEN system inside the bigger New Zealand power system, from the generating station, through the national grid and local distribution network, right down to the switchboard, socket, outlet, and appliance. More importantly, you should be able to reduce an MEN fault back to a simple circuit and explain what the protective device will do. Here is our route. First, we will look at the big picture. Second, we will find the neutral point. Third, we will explain what MEN means. Fourth, we will trace normal current and fault current. Finally, we will examine common faults, testing ideas, and misunderstandings. Let us begin by stepping back and looking at where the MEN system fits within the whole New Zealand electricity system. Electricity must be generated at the same time that customers are using it. New Zealand obtains electrical energy from hydro, geothermal, wind, thermal generation, solar generation, and other sources. Different power stations use different energy sources, but the large electrical generators normally produce three-phase alternating current. At or near a generating station, transformers usually step the voltage up. High voltage allows the same power to be transmitted with lower current. Lower current reduces I2R losses and reduces voltage drop. On the national grid, Important alternating current transmission voltages include 110 kV and 220 kV. The North and South Island systems are also connected by the high voltage direct current link between Benmore and Haywards. Transpower owns and operates the national grid and also performs the system operator role. At grid substations, electricity is delivered to local distribution companies, sometimes called lines companies. The voltage is stepped down for regional and local distribution. The exact voltage sequence depends on the network, but 33 kV and 11 kV are common distribution levels. Closer to customers, a local distribution transformer steps the voltage down again. Its low-voltage secondary normally supplies 4 conductors, 3 line conductors, L1, L2 and L3, and a neutral conductor. The nominal voltage is 400 volts between any two lines and 230 volts between any line and neutral at 50 Hz. A house normally receives one line and neutral, giving a 230 volt single-phase supply. A larger commercial or industrial installation may receive all 3 lines and neutral, giving both 230 volt single-phase loads and 400 volt three-phase loads. Now separate two ideas. A retailer sells electricity and manages the customer account. The physical path of the electricity is through generators, Transpower's grid, a local distribution network, and the customer's installation. For an electrician studying the MEN system, our main focus is the physical network and the protective earthing arrangement. Now that we have followed electricity from generation to the customer, let us move closer to the distribution transformer and find where the neutral comes from. To understand MEN, we must first understand the neutral. Picture the low-voltage secondary windings of a 3-phase distribution transformer connected in star. One end of each of the 3 windings is joined at a common point. That common point is the star point, and it becomes the neutral point. From each line conductor to the neutral point, the nominal voltage is 230 volts. Between 2 line conductors, the nominal voltage is 400 volts. This is because the 3-phase voltages are separated by 120 electrical degrees. The line-to-line voltage is the line-to-neutral voltage multiplied by the square root of 3. For a single-phase load, current leaves the transformer on a line conductor, passes through the load, and returns on the neutral conductor. For a balanced 3-phase load, such as an ideal balanced motor, the phase currents return through the other phases and the neutral current can be approximately 0. For unbalanced single-phase loads connected across the 3 phases, the neutral carries the vector sum of the out-of-balance currents. Quick check. In normal operation, should the protective earthing conductor carry the load current? No. Normal load current should return through the neutral or through the other phase conductors. The protective earthing conductor is there for safety under fault conditions. Keep that distinction in your mind. Neutral is a normal current carrying conductor. Protective earth is not normally a load current conductor. Before we go further, let us ask why the transformer neutral point is connected to earth at all. Now imagine that the transformer secondary is completely isolated from earth. There is no deliberate connection between the star point and the general mass of Earth. Line-to-line and line-to-neutral voltages can still exist, but the complete system has no fixed reference to Earth. If the first line-to-earth fault occurs on an ideal isolated system, the current may be too small to operate an overcurrent protective device. At the same time, the voltages of the other conductors relative to Earth can shift. A system that appeared normal can now have unexpected voltages to Earth. If a second Earth fault develops on another line, a dangerous line-to-line fault path can be created through the earthing system. In the New Zealand public low-voltage distribution system, the neutral is deliberately connected to Earth. This fixes the neutral point close to Earth potential and gives predictable line-to-Earth voltages. It also allows exposed conductive parts in an installation to be connected back to that Earth neutral through the protective earthing system. But the neutral is not earthed at only one place. It is earthed at the source, at regular points in the distribution system, and at connected electrical installations. That is why the system is called multiple earthed neutral. With that background, we can now define the MEN system more carefully. MEN stands for multiple earthed neutral. AS/NZS3000 defines it as an earthing system in which the parts of the installation that are required to be earthed are connected to the general mass of Earth, and are also connected within the installation to the supply neutral, or PEN conductor. Inside the installation, the protective earthing conductor is separated from the neutral conductor. Internationally, this general arrangement is described as TNCS. The letters give us a useful memory aid. T means that one point of the supply system is directly connected to Earth, normally the neutral point of the supply transformer. N means that exposed conductive parts are connected to that earthed point of the supply. C means that, in part of the system, the protective and neutral functions are combined in one conductor. S means that, within the installation after the MEN connection, the neutral and protective earth functions are separated into different conductors. The New Zealand MEN arrangement and the international TNCS arrangement are the same in principle, although the detailed rules and terminology are not identical. For New Zealand installation work, we use the requirements of the applicable New Zealand legislation, AS/NZS3000, and the relevant distributor requirements. Next, let us walk through the main physical parts of the MEN earthing arrangement one by one. AS/NZS3000, clause 5.3.1, gives us a very useful list. For an installation connected to the MEN distribution system and protected by automatic disconnection of supply, the protective earthing arrangement includes 6 main parts. Part 1 is the protective earthing conductors. These connect exposed conductive parts, such as the metal case of Class 1 equipment, back to the earthing system. Their job is to carry fault current safely. They should not normally carry load current. Part 2 is the main earthing conductor. This runs from the main earthing terminal, or earth bar, at the main switchboard to the earth electrode. It should be run as directly as practicable, and its connection at the electrode must be accessible for inspection and testing. Part 3 is the main earthing terminal, connection or bar. This is the central connection point for the protective earthing conductors, the main earthing conductor, the MEN connection, and required bonding conductors. Part 4 is the MEN connection, commonly called the MEN link. At the main switchboard, it connects the main earthing bar to the main neutral bar. This single connection is the bridge that joins the installation protective earthing system to the supply neutral. Part 5 is the earth electrode. It connects the installation earthing system to the general mass of Earth. In New Zealand, a vertical electrode must meet the type, material, dimension and installation requirements of the wiring rules, including the required minimum driven depth. The electrode also needs a suitable location and an accessible connection. Part 6 is equipotential bonding. Bonding connects required extraneous conductive parts to the earthing system so that dangerous voltage differences are reduced. The purpose is not simply to make every piece of metal earth. The purpose is to keep simultaneously accessible conductive parts at substantially the same potential during a fault. Try to say the 6 parts now. Protective earthing conductors, main earthing conductor, main earthing terminal or earth bar, MEN connection, earth electrode, and equipotential bonding. Now that we know the parts, let us use them to trace current. We will begin with normal load current because we must understand the normal path before we can understand the fault path. Consider a 230 volt heater connected to L1 and neutral. Current leaves the transformer winding on L1. It travels through the distribution line, service connection, consumer mains, main switch, circuit protective device, and final subcircuit active conductor. It passes through the heater element, then it returns through the final subcircuit neutral, neutral bar, main neutral, and supply neutral back to the transformer star point and through the transformer winding. The protective earthing conductor is connected to the heater's metal case, but in normal operation, no load current should flow through it. The MEN link is present, but it is not intended to divert normal final subcircuit current onto the protective earthing conductors. This is why neutral and earth must remain separate downstream of the main MEN connection. If someone installs another neutral to earth link at an ordinary distribution board, some normal neutral current can divide and flow through protective earthing conductors, cable armour, metal pipes, or other bonded metal. That creates touch voltage, heating, corrosion, and RCD problems. Now we are ready to return to the fault from the beginning of the lesson and trace the complete fault current circuit. In our metal-cased appliance, the active conductor touches the metal case. Because the case is connected to the protective earth, this is no longer only a dangerous live case. It becomes a low-impedance active-to-earth fault. Trace the fault current slowly. First, current leaves the transformer winding and travels along the active conductor to the fault. Second, it passes from the active conductor into the metal case. Third, it flows along the appliance protective earthing conductor and the circuit protective earthing conductor to the earth bar at the switchboard. Fourth, it crosses the MEN link from the earth bar to the neutral bar. Fifth, it returns along the main neutral and the supply neutral, or PEN path, to the transformer star point. Finally, it passes through the transformer winding, completing the loop back to the active conductor. We have now traced the physical route. The next step is to turn that route into the simple equivalent circuit that we can analyze with Ohm's law. Reduce that complete route to a simple circuit. The transformer source, active path, faulted case, protective earth, MEN link, and neutral, or PEN return, are series parts of one closed fault loop. Include the relevant source, conductor, and connection impedances to obtain the complete earth fault loop impedance, ZS. Let us use a simple teaching example. Suppose the measured or calculated loop impedance is 0.5 ohms. The nominal voltage is 230 volts. Using Ohm's law, fault current equals 230 divided by 0.5. That gives approximately 460 amps. Now compare 460 amps with a 16 amp MCB. The fault current is nearly 29 times the rated current. That is why we expect a common MCB to operate very quickly. But do not guess the exact trip time from the rating alone. Check the type and the manufacturer's time current curve, or apply the applicable wiring rules method. The calculation gives us the evidence for the next step. This example is illustrative. A real installation uses its actual loop impedance and the actual protective device characteristic. The important reasoning is universal. Low ZS gives high fault current, and high fault current gives fast overcurrent device operation. Which single component connects the earth bar to the neutral bar at the main switchboard? The MEN link. Which conductor normally carries the fault current from the appliance case back to the switchboard? The protective earthing conductor. Which conductor normally carries the return from the switchboard to the transformer? The supply neutral or PEN path. Before moving on, we need to clear up one of the most common sources of confusion: the difference between the metallic fault current path and the path through the soil. The word earth can cause confusion. Students often imagine that every earth fault current travels down the local earth electrode through a large distance of soil and then back to the transformer electrode. Some current can take that parallel route. However, soil usually has much higher impedance than the metallic neutral and PEN path. Therefore, in a healthy MEN installation, the main intended low-impedance fault current path is through the protective earthing conductor, MEN link, and supply neutral back to the transformer. The earth electrode connects the system to the general mass of earth, helps establish an earth reference, and contributes a parallel path. It is an essential part of the system, but it should not be described as the only or main conductor that operates the circuit breaker. AS/NZS 3000 makes another important distinction. It does not specify one universal resistance to earth value for the individual earth electrode of an installation connected to an MEN system. The combined earthing system must satisfy the earth fault loop impedance requirements. Separately, the resistance of the main earthing conductor from the main earth bar to the electrode, including the connection, has its own maximum value in the standard. So when you see an earth stake, do not think, this is the complete fault return system. Think, this is one required part of the MEN earthing arrangement, connected through the main earthing conductor to the earth bar and MEN link. This brings us to the protective principle called automatic disconnection of supply. The protective principle is not simply connect metal to earth. The complete principle is connect exposed conductive parts to a reliable low-impedance fault path, then use a protective device that disconnects the supply within the required time. For a circuit protected by a fuse or circuit breaker, the earth fault loop impedance must be low enough to produce sufficient fault current. A lower loop impedance gives a higher fault current. A higher fault current normally makes an overcurrent device operate faster. For a 230 volt supply, the wiring rules specify maximum disconnection times for different circuit types. Common examples are 0.4 seconds for final sub-circuits supplying socket outlets up to 63 amps, handheld Class 1 equipment or portable equipment intended to be moved during use, and up to 5 seconds for other circuits where the stated conditions are met. An RCD uses a different detection principle. It compares the current leaving through the live conductors with the current returning through them. If some current leaks through a person or an unintended earth path, the currents no longer balance. The RCD can disconnect at a much lower leakage current than the current required to operate an ordinary circuit breaker. However, an RCD is additional or fault protection for the situations required by the rules. It does not remove the need for correct earthing, correct overcurrent protection, correct conductor selection, correct polarity, or a sound MEN connection. Now let us connect this fault loop idea back to the words multiple earthed neutral and explain why the neutral is earthed at several places. The neutral is earthed at the transformer, at points along the distribution network, and at connected installations. These multiple connections help hold the distribution neutral close to earth potential and provide parallel connections to the general mass of Earth. Multiple earthing can reduce the overall impedance to Earth and helps control system voltages relative to Earth. It can also provide some resilience when one earth connection is poor. But it does not make a broken neutral safe, and it does not allow us to ignore the integrity of the metallic neutral conductor. This is a very important professional attitude. The neutral in an MEN system is a safety-critical conductor. A loose or broken neutral can create dangerous voltage conditions even when the active conductors appear normal. Next, let us move from the supply network into the installation and look carefully at where the MEN link belongs. In a normal installation, the MEN connection is located at the main switchboard. Downstream distribution boards have separate neutral and earth bars, but no extra MEN link. Why only one deliberate neutral to earth connection within that installation? Because after the main switchboard, neutral carries normal load current and protective earth is reserved for safety. A second link creates parallel paths for normal neutral current through the earthing system. There are permitted arrangements for a separate MEN installation in an outbuilding, and there are special arrangements for owner-operated substations or distributor-provided earthing terminals. These are designed systems with specific conditions. They are not permission to add a neutral-to-earth link wherever it seems convenient. When reading a diagram, locate the point of supply, the main switchboard, the main neutral bar, the earth bar, the MEN link, and the earth electrode. Then check where neutral and protective earth become separate. This gives you the electrical map of the installation. Once the healthy arrangement is clear, we can use the same simple circuit method to understand what happens when something goes wrong. There are 5 important failure conditions to consider. First, a missing MEN link. Do not answer this problem only by saying, the MCB may not trip. Draw the simple equivalent circuit again. The protective earthing conductor still reaches the earth bar, but the low impedance metallic bridge from the earth bar to the neutral bar is open. The fault current may now depend on higher impedance parallel paths through the main earthing conductor, electrodes, soil, and other network connections. Those impedances are variable, so the following number is only a teaching example. If the remaining loop impedance were 40 ohms, Ohm's law gives 230 divided by 40, or about 5.75 amps. 5.75 amps is below the normal load rating of a 16 amp MCB, so that MCB would not trip from overcurrent. The metal case could remain at a dangerous touch voltage. This is the consequence of the broken circuit path. The impedance rises, fault current falls, and automatic disconnection may fail. That conclusion is about the MCB's overcurrent function. If the circuit has a correctly installed and functioning RCD, the RCD uses residual current imbalance and may disconnect even though the current is too low to trip the MCB. Correct RCD protection still does not excuse a missing MEN link. Second, a loose or high-resistance protective earth connection. The fault loop impedance increases, fault current falls, and the protective device may take too long to operate or may not operate as intended. Use the same method for that second fault. Replace the good connection in your equivalent circuit with its higher impedance. Add the complete loop impedance, calculate I equals V divided by Z, and then compare the answer with the protective device curve. A different fault, but the same fundamental reasoning. Third, an unwanted neutral to earth link at a downstream board. Normal neutral current can flow through the protective earthing system and bonded metal. This can create shock risk, interference, and nuisance RCD operation. Fourth, a broken or high-resistance supply neutral. In a single-phase installation, the installation neutral and bonded earthing system can rise above local earth potential through connected loads. In a three-phase, four-wire system, an open neutral can also cause severe voltage imbalance. Some single-phase loads can receive undervoltage, while others receive dangerous overvoltage. Multiple earths do not guarantee safety because the soil path may have significant impedance. Fifth, a damaged or disconnected main earthing conductor or earth electrode connection. The installation loses an important part of its connection to the general mass of earth. This is why the connection must be mechanically sound, protected against corrosion and damage, accessible for inspection, and labelled against disconnection. We have discussed the parts separately. Now let us put them together by walking through a typical New Zealand house from the incoming supply to one appliance. Imagine you are standing outside a typical New Zealand house. Electricity has arrived through the local distribution network. Depending on the area, the service may be overhead or underground, and it may pass through a boundary box or service pillar before reaching the meter and main switchboard. At the main switchboard, identify the incoming active conductor or conductors, the main neutral, the main switch, service and circuit protection, the main neutral bar, the earth bar, and the MEN link. From the earth bar, the main earthing conductor runs to the earth electrode. Protective earthing conductors leave the earth bar with the final subcircuits. Required bonding conductors also connect to the earthing system. Now follow one socket outlet circuit. The active passes through its protective device, the neutral returns to the neutral bar, the protective earth returns to the earth bar. At the socket outlet, the active and neutral deliver power to the appliance. The protective earth connects the accessible metal case to the fault path. If the appliance is healthy, current goes out on active and back on neutral. If active touches the case, the protective earth changes from a normally non-current carrying safety conductor into a fault current conductor. It carries the fault to the earth bar, through the MEN link, and back by the supply neutral to the transformer. The protective device disconnects the supply. That is the complete story from the national grid to the appliance case. The large power system delivers energy. The MEN earthing system controls the consequences of a fault inside the installation. A correct explanation is important, but an electrician must also prove that the real installation matches the explanation. This is where inspection and testing become essential. A diagram can look perfect, while a real connection is loose, corroded, missing, or connected to the wrong bar. That is why inspection and testing are essential. Before connection or after relevant work, the installation must be verified in accordance with the applicable requirements. The electrician checks the presence, location, identification and security of the MEN link, continuity of the earthing system, the main earthing conductor and electrode connection, polarity, insulation resistance, earth fault loop impedance where applicable, and RCD operation where RCDs are installed. The order and method of testing matter. Some tests are carried out with the supply isolated, while others require controlled live testing by a competent person using appropriate equipment and procedures. Do not copy a test sequence from memory without checking the current standard and your safe working requirements. The purpose of testing is to prove the safety concept we have learned. Is the protective earth path continuous? Is neutral separated from earth downstream of the correct MEN connection? Is the fault loop impedance low enough for the protective device? Does the RCD disconnect correctly? These tests turn a drawing into evidence. Before we review the lesson, let us correct 6 common misunderstandings that can prevent students from seeing the complete circuit clearly. Misunderstanding 1. Neutral and earth are the same wire. Not within the installation. They are connected at the MEN point, but they have different functions and must be separated downstream. Misunderstanding 2. The earth electrode carries all fault current. No. In a healthy MEN system, most fault current normally returns through the metallic protective earth MEN link and neutral or PEN path. The soil path is parallel and usually has higher impedance. Misunderstanding 3. An earth wire has no voltage, so it can never be dangerous. During a fault, a protective earthing conductor carries current and can develop a voltage because every real conductor has impedance. A broken neutral condition can also raise the complete earthing system above local earth potential. Misunderstanding 4. An RCD replaces earthing. No. RCD protection and the protective earthing system work together, but they perform different functions. Misunderstanding 5. More neutral to earth links must make the installation safer. No. Uncontrolled extra links allow normal neutral current to flow through protective earthing paths. Misunderstanding 6. If an isolated system has no deliberate earth connection, touching one live conductor is always safe. No. Real systems have capacitance, leakage, faults, and accessible conductive parts. The safety of isolated or IT systems depends on deliberate design, monitoring, and specific requirements. Never use a simplified classroom diagram as permission to touch a conductor. We have now reached the review. I will ask 13 short questions and then give each answer, so use each question to check whether you can rebuild the system in your own mind. Question 1. What is the physical journey of electricity to a house? Generation, high voltage transmission on the national grid, local distribution, a distribution transformer, the service connection, the main switchboard, and then final subcircuits. Question 2. Where does the neutral originate? At the star point of the transformer's low voltage secondary windings. Question 3. Why is the system called multiple earthed neutral? Because the distribution neutral is connected to Earth at the source and at multiple other points, including connected installations. Question 4. Where is the MEN link normally located? At the main switchboard, between the main neutral bar and the main earthing bar. Question 5. Should protective earth carry normal load current? No, it is a fault protection conductor and should not normally carry load current. Question 6. Trace an active to case fault. Active, faulted case, protective earth, earth bar, MEN link, neutral bar, supply neutral or PEN, transformer star point, and transformer winding. Question 7. What is the role of the earth electrode? It connects the earthing system to the general mass of Earth, establishes an Earth reference, and contributes a parallel path. It is not normally the main metallic fault current return path. Question 8. What makes automatic disconnection work? A reliable low-impedance fault loop together with a protective device that disconnects within the required time. Question 9. What four-step method should you use for an MEN fault question? Draw the complete loop, add the impedances, calculate I equals V divided by Z, and compare that current with the protective device's operating requirement. Question 10. If ZS is 0.5 ohms at 230 volts, what is the prospective fault current? Approximately 460 amps. Question 11. Why may a missing MEN link prevent a 16 amp MCB from tripping? The intended metallic loop is open, so loop impedance can become much higher, and the resulting fault current may be below the MCB's operating current. Question 12. Why must neutral and earth remain separate downstream of the MEN link? To prevent normal neutral current from flowing through protective earthing conductors and bonded metalwork. Question 13. Why is a broken neutral dangerous? It can raise the installation earthing system above local earth potential and, on a 3-phase, 4-wire system, create damaging or dangerous voltage imbalance across single-phase loads. That completes our review, so let us finish by bringing the whole lesson back to one central idea. The New Zealand MEN system connects exposed conductive parts to the earthed supply neutral through a controlled low-impedance path, so that a fault causes rapid automatic disconnection of supply. Remember the two current paths. Normal current returns through neutral. Fault current from exposed metal returns through protective earth, the MEN link, and the supply neutral to the transformer. Then remember the method. Draw the loop, calculate the current, and prove why the protective device will, or will not, operate fast enough. Thank you for listening. Before you move on, draw the complete system from the transformer to one metal-cased appliance. Label every conductor in the normal current path and fault current path. Add reasonable impedance values, calculate the fault current, and state what information you need to confirm the MCB trip time. If you can do that without notes, you have built the right big picture.